Welcome to The Explainer. Today, we're taking a look at one of the absolute most elegant and honestly high-stakes puzzles in modern science, and that is organic synthesis. If you've ever found yourself wondering how scientists create the incredibly complex chemicals that basically make up our modern world, well, you are definitely in the right place. We're going to look at how chemists essentially act as molecular architects using a pretty genius process of reverse engineering to solve structural problems that literally look impossible at first glance. Think about it for a second. We rely on pharmaceuticals every single day. But these incredibly complex, life-saving structures, they don't just magically appear out of nowhere, right? So how exactly do chemists build them completely from scratch? They have to be pieced together from much simpler, cheaper, and readily available starting materials. And as you'll see, pulling that off requires an incredible amount of strategy. To really put the monumental challenge of doing this linearly into perspective, just consider this staggering number. 100. That's how many steps it took to complete the historic total synthesis of vitamin B12. Achieved back in 1972, this singular project required over 10 years of intense collaboration and the grueling day-in, day-out work of 91 postdoctoral researchers and 12 PhD students. It really hits the nail on the head when we talk about just how painstakingly difficult standard, forward-moving synthesis can be when you're relying purely on human effort. Okay, let's dive into this. Here is our roadmap. 1. Building molecules from scratch. 2. The logic of retrosynthesis. 3. The chemist's toolkit. 4. Reverse engineering everyday medicines. And 5. AI in drug discovery. Starting off with Section 1, building molecules from scratch. At the end of the day, the fundamental goal of any good synthesis is just brutal efficiency. We want to convert cheap, easily available starting materials into a specific, desired product. And we've got to do it using the fewest possible steps to get a really high overall yield. Now, you might be wondering, with millions of known organic compounds out there, how do they keep it all straight? Well, chemists don't actually memorize millions of individual reactions. Instead, they focus on what we call functional groups. These are specific groupings of atoms that dictate exactly how a molecule is going to behave. Think of them like the predictable handles or connectors on a custom piece of machinery. By identifying these functional groups, chemists can reliably map out how to build a target molecule, which is absolutely crucial for developing everything from new food additives to vital medicines. Moving right along to Section 2, the logic of retrosynthesis. Because, when a target molecule is unbelievably complex, trying to build it straight from scratch is kind of like navigating a maze blindfolded. You definitely need a better strategy. So, what does this all mean? The crucial point here is understanding the stark difference between synthesis and retrosynthesis. In standard synthesis, you start with a simple material and you try to forge a path forward to your complex target molecule. Retrosynthesis is exactly the opposite. It is a straight-up reverse engineering approach where you start with your final, complex target molecule and you mentally break it down, step by step, into simpler, much less complicated compounds until you arrive at something that's readily available. Notice that top pink arrow right there? That open-ended arrow with the double lines? That is the universal symbol for retrosynthesis. It implies a process of imaginary breaking down. You aren't actually running a reaction backward in the lab, you're just systematically deconstructing the molecule on paper to plan out your route. Which brings us to Section 3, the chemist's toolkit. Taking these molecules apart requires a highly specific vocabulary. Our first tool is the disconnection. This is the actual analytical process of that imaginary breaking down we just talked about. Think of your target molecule like a massive, incredibly complex Lego castle. A disconnection is just the mental exercise of pulling apart specific, strategic blocks to figure out how the whole thing was assembled in the first place. Now, when you actually perform a disconnection and conceptually break a bond, you're left with fragments called synthons. These are basically the core building blocks of your synthesis. However, here's the catch. These fragments are usually unstable ionic species. That means they carry a positive or negative charge. Sure, they exist on paper, but there's no way you could just walk into a lab and pick up a bottle of synthons. Because those synthons are so unstable, chemists have to identify their synthetic equivalents. A synthetic equivalent is simply the stable, real-world reagent that you actually buy from a chemical supplier and physically use in the lab. It basically acts as a stand-in, perfectly carrying out the exact chemical function of your imaginary synthon. And this brilliantly illustrates our final tool, functional group interconversion, or FGI for short. Just look at this massive roadmap for aliphatic or straight-chain compounds. An alcohol can seamlessly become an aldehyde, an alkene, or halogenoalkane. It's essentially a vast, interconnected web of potential pathways that chemists use to cleverly maneuver around structural roadblocks. And hey, aromatic compounds, those are the ones containing benzene rings, they have their own highly organized interconversion maps too. Starting from something like toluene or nitrobenzene, chemists use these precise pathways to reach a wide variety of target structures. Having these mental maps internalized is a total game changer. It allows chemists to design highly efficient routes, letting them find the absolute best starting material for their specific target.
All right, on to Section 4, Reverse Engineering Everyday Medicines. Let's take all these conceptual tools out of the textbook and apply them directly to the stuff sitting in your medicine cabinet.
The real beauty of organic synthesis is that it takes a terrifyingly complex structure and makes it totally achievable. For pharmaceutical compounds, the procedural steps are always exactly the same. We systematically disconnect the bonds, we identify the real-world synthetic equivalents, and we use functional group interconversions to smooth out our path backward. Let's look at a super common painkiller to see this in action. Now, what's really interesting about this slide is how elegantly paracetamol is deconstructed. By disconnecting the carbon-nitrogen bond, we get two distinct synthons. These easily translate into the real-world reagents 4-aminophenol and an acyl chloride. From there, a quick interconversion turns the amino group into a nitro group, and suddenly, boom, one more disconnection drops us all the way back to phenol, which is a super cheap and highly available starting material. Now let's try applying this exact same logic to aspirin, a completely different chemical structure. If we trace its retrosynthetic tree, disconnecting the ester linkage to get salicylic acid, and then disconnecting the carbon-carbon bond of the carboxylic group, well, we find something pretty amazing. The synthetic equivalents point us right back to phenol again. Think about that. Two entirely different medicines, perfectly reverse engineered down to the exact same simple starting block. And finally, Section 5, AI in drug discovery. The logic of retrosynthesis absolutely drove the 20th century. But the future? Well, it's moving way faster than is humanly possible. Developing new drugs, especially things like antibiotics, has traditionally been incredibly costly, time-consuming, and honestly pretty limited in scope. But artificial intelligence is completely changing the game. Here's a great example. Researchers at MIT were facing a massive problem. Pathogens were becoming increasingly resistant to all of our existing antibiotics. To find a new solution, they designed a machine learning algorithm. But they didn't just tell the computer what existing drugs looked like. No, they trained the model to actively look for the underlying chemical features that make molecules effective at killing bacteria. They initially trained and applied this model on a set of 2,500 molecules and 800 natural products. And the AI delivered. It picked out one specific molecule that structurally looked absolutely nothing like our existing antibiotics. Using another model, they confirmed it would likely have low toxicity in humans, and they named it halicin. Just take a look at the Petri dish images here. When tested against isolated strains, halicin successfully cleared out some of the world's most problematic treatment-resistant bacteria. But guys, here is where the true power of this technology becomes mind-blowing. After successfully identifying halicin, the researchers unleashed their computer model on a significantly larger database. The AI screened more than 100 million molecules. And get this, it completed that entire screening in just 3 days. From those 100 million, it identified 23 more potential candidates featuring entirely new structures. So to put that all into perspective, we've gone from a 10-year, 100-step synthesis requiring nearly 100 scientists just for a single vitamin to an AI screening 100 million molecules over a long weekend. The chemist's toolkit of retrosynthesis gave us the map of the physical world, and AI is now supercharging our ability to explore it. So I'll leave you with this thought. If AI can scan 100 million molecular structures in just 3 days, what previously impossible cures are waiting to be synthesized tomorrow? Thank you so much for checking out this explainer, and keep exploring.